Let us now try to understand the buck converter. So there is this unregulated voltage source Vi here, and this is the single pole double throw switch, an inductor followed by capacitance. Now these blue portions are the inside components of the buck converter. The black portion are external, not under your control for design, and this is the load. So let us complete. Now this is the buck converter circuit we have seen and discussed. Let us try to understand it a bit more in detail. This is the pole, this is throw 1, this is throw 2, L, C, R0, Vi, unregulated. This is DTS, meaning that pole and throw 1 are connected for DTS period of time. Pole and throw 2 are connected for 1 minus DTS period of time. This is V0, this is I0, this is IL, inductor current, and this is IC, the capacitor current. Let us also indicate the voltage VL across the inductor. Now let us try to understand the circuit visually, graphically, by looking at the waveforms. So I am going to have the time on the x-axis, and the time is split into DTS, 1 minus DTS, DTS, 1 minus DTS, two switching periods. So let us first draw a waveform Vp with respect to time. So during DTS, P is connected to T1, so it is Vi, Vin. Then during 1 minus DTS, P is connected to T2, it is 0. Then during DTS connected to Vin, and so the waveform at the pole P, Vp is given here. So it is Vi and Vi. Next, let us try to draw the voltage VL. This also we have seen. So during the time DTS, when the pole P is connected to T1, Vp is Vi, and on the other side of the inductor it is V0. Vi minus V0 is appearing here. And here when P is connected to T2, Vp is 0, and on the other side you have V0 and you have minus V0 coming across the inductor. So it repeats every cycle in this fashion. Next, let us have a look at IL, the current through the inductor. Now the current through the inductor has two components. One component, the I0 component, other component, IC component. See, the I0 component is a DC current, average current, so it has to flow through R0 because capacitor current cannot have an average. So entire DC current or the average current goes through R0, and the average zero current flows through IC. So if you look at these two parts, let us say this DC part is I0, and the AC part, the part that flows through IC, is given in this form. Let us say we draw this line. How did I get this line? So that is obtained from the Faraday's law. Voltage across the inductor is given by L dIL by dt. So this means that dIL by dt has a slope of VL by L. Now if you see here, the voltage VL during the DTS period is a fixed constant value Vi minus V0. So it is constant. So Vi by L, L is a constant. So Vi by L is a constant. So therefore the slope of dIL by dt has to be fixed. Therefore a straight line, having a slope Vi minus V0 by L. Now during this time, the voltage applied across the inductor is negative, and the slope will be minus V0 by L, and because it is minus V0 by L, it's a negative slope. So minus V0 by L, positive slope, negative slope, so on, it keeps going. Next, Let us have a look at IC, the capacitor current. See, I0 is the fixed DC value. Remove the I0 component from IL. What remains is the AC part, so the ripple part. So you will see the IC or the capacitor current contains the zero average portion or just only the ripple portion of the current of the inductor current. So it will have the same ripple envelope wave shape. Average is 0. Next, let us look at current through T1P. When pole is connected to T1, there will be a current flow. When the pole is not connected to T1, current flow is 0. So let us say T1P in this direction. So you have, let me draw this I0 level, because it is the inductor current that has to flow either through T1 or through T2. So the level, the inductor current has to be, level has to be the same. So this portion of the inductor current, which I am indicating, will flow through T1P. So let us indicate that. And this portion of the inductor current will not flow through T1P, because during that time, 1 minus dTs time, T1 is not connected. So T2P, if you see, is mutually exclusive with T1P. You will see that the current flows during the other portion, 1 minus D portion. So this portion of the inductor current flows through T2P, that is here. So the inductor freewheels in this fashion. So when the T1P is connected, inductor is charging up like this, it is going up, inductor is charging up, and then when it moves in this fashion, and when pole is connected to T2, inductor is discharging, it is falling, so it is freewheeling through this. So the current flow is in the direction T2 to P. Current flows in the direction T2 to P. So if you take the inductor current peak to peak ripple, we will call that as delta IL. So if you take the peak value of the current flowing in T1P, it is I0, level I0, plus delta IL by 2. This from here to here is delta IL. So from level I0 to peak, it is delta IL by 2. So this can be used for designing the switches, rating the switches. Then let us look at voltage across T1P. These are all useful waveforms to rate the switches. So during the time when DTS T1P is connected, 0 voltage. When it is not connected, P is connected to T2, so P is at 0 potential, T1 is at VI potential, it has to support VI during the off condition. So this is the voltage across T1P. Voltage across T2P. So voltage across T2P, so actually voltage P is more positive compared to T2. So during the time when T1 is connected to P, P is at a positive potential compared to T2, because T2 is always at ground. Therefore, P being more positive, I am putting it as VPT2. Voltage is from P to T2. So it is supposed to withstand VI here, 0, VI and 0 in this fashion. So these are the important waveforms that you should obtain even on an oscilloscope when you use the buck converter circuit.